Hello everyone. So today we are going to do question combination sum. Basically this is a question for recursion and backtracking. So before doing this question, let me explain you what does this question want to convey. So basically here we are given with an array of distinct integers candidates, means this is that array. Here integers are distinct, no duplicates are there, and one target sum is given to us, and we are required to return a list of unique combinations of candidates with the chosen number sum to target. Basically, when we choose this 2, 2, 3, then we add up, it simply adds up to the 7. Then 7 itself adds up to 7. So like this, we are required to return all the possible combinations, which could even include the duplicate of a particular number, which add up to simply 7. So like this, in this example also, we are required to give all the possible combinations will simply add up to this particular target, either by duplicating a single number or by duplicating a single number with combination of other numbers, or both of them be distinct, or even a single number could be taken. So these are uh, various outputs which could be there. Now, before thinking about what the code could be, let me walk you through the explanation of this question through a recursion tree. So basically, let me take the example. Let me draw this tree again itself so that I could explain you in better manner. So here we are given. Let us take the example that we are given with this array, and our target is simply 5, right? So how a recursion works is it simply goes into deep and deep if we are performing it in the form of DFS, right? So it will simply go into deeper and deeper and then simply backtrack. This is how recursion would work here. If we take a function in such a manner, I'll explain you for that part also, that how we would be deriving its solution. Now here, when we'll take this particular one, then what we would be doing, we'll simply subtracting it from the target, right? And it will simply push that one to our answer array. Now next thing, we'll go into more deep and check for other possible combination which could be there. So we'll simply subtract again 1, and then we'll go into more deeper and subtract 1 again, and then again, right? And then again, we will be doing like this. So at the end, we'll get a combination where all ones are there, right? So they simply add up to 5. So this is one of the possible combination. Now it will simply backtrack and check for other possible combinations with other numbers of the array, right? So when it simply backtracks, so here it comes up and check 1 minus 2. It is not possible, right? So here it is not possible. So again it returned to its parent caller. Now when it comes here, so no further call is left, which could simply give a valid answer. So that's why it again backtracks. So at this position, we are having 2 and 2, right? So now, yes, a possible combination could be made. So here it will simply add this to the answer. Means that vector of vector int, the final answer was there. Means the final result which was there, it will add up this particular vector to that final result vector. Now it will check for others, but here it will simply see that, yeah, here answer is simply negative, so that's why it will simply backtrack. And here when it backtracks, so here it checks that here is 3 minus 1, right? So here it will be simply 3 minus 2, means checking for other possible combinations. And basically this particular checking for other possible combinations is because of for loop only. Because of for loop only, it will simply traverse the whole array which is being given to us, and going into deep of a particular branch is because of the recursive calls which would be there. And we here could simply see that all these recursive calls are in such a manner that it is including the previous number which was there, which simply indicates that a code would be simply like that. It will be pushing this I and it will be pushing this target minus nums of I. That's why means these two things would be there in our code. That's why our recursion tree is simply forming in this manner, right? And all this which is coming up in this direction, it is all because of a for loop only. So that's why when it backtracks, so it checks that are there some elements which are being left in a for loop, right? So it will check up here, and if it found the valid combination, because here it will check like this, and then it will check that 1 minus 2. It is not a valid combination, right? So that's why it will simply return false to its parent caller and then to its parent caller again. And one more call was left, right? 3 minus 3. That was left. So it will simply do that particular. And now our target is simply equals to 0 at this particular position, right? So we have reached our base case at this moment, and this is our array which is there. So that's why this particular would be simply pushed to our result. So this is one more valid combination. So now after pushing this particular to result, then it will simply, what it will be doing is, it will simply backtrack. Here it won't backtrack basically. Here it will simply return to its parent caller, that is this particular, and it now parent caller will check, is there any further elements being left in our loop, means through that loop, means in our array. So it says that no. So it will, what it will do, it simply backtracks again to its parent caller. And now here parent caller checks that yes, I'm having some more elements left. So now it will check those elements, right? So 1, 2 would be pushed, and now it will again check into deep of this particular array, right? So that's why now it will work. Earlier it was 4 minus 2. Now target would be simply 2, right? So first we'll start from that particular element only from which it was coming. That is from this one. So that's why it subtracts 2 from there, and now it adds up 1, 2, 2 here, right? And now as it has reached the target equals to 0, so that's why it will simply push this particular into our result vector, right? Now after pushing, it will simply return to its parent caller, right? And its parent caller will check that are there some valid combinations left. So here it will be negative, so no, there is nothing valid left, right? So now if we encounter negative here, so it won't go further, and it will now return to its parent caller again. That is, it will return here. Now 4 minus 2 was done. Now comes the part of 4 minus 3. Basically 3 was also left in the array, right? So here it will simply push here, and then it will go further into D. After doing 4 minus 3, now comes up 1 minus 3 again, so which is a negative number. So that's why now it won't move further, and it will return back to its parent, right? And then it will return back to its parent, right? So it reaches this particular call, and then it returns to the main array. This means main caller function, right? When it returns there, then it checks that are there further elements left at this particular state of recursive call. Then it says yes, because we are still left with 2 and 3, right? So that's why now the call would be of 5 minus 2 branch. So here 2 would be pushed, right? And then for all the things which was being done for this particular call, then every other thing would be done for all others also. So I have made the whole recursion tree for the same. I can see that and analyze that how it is being done. So this is the one which I had made. So basically here what it was like, that it has simply moved down to the branch of this particular one and got this answer, then this answer, means all the ones whom I have ticked, it got all those answers there, right? So this is how the question was required to be done using this recursive tree. Means basically how using the recursion we could get the answer. Now comes the part of coding. Like before coding, what we can do is, like, because it is a recursive question, so what are the things which are being required in recursion, right? While explaining with that recursive tree, I've explained you that how that base case would be there and things. So for any recursive solution, we are required with a base case, right? So in that recursive tree only we were viewing that when target equals to 0, right? Then we were required to push our answer right into the main result. So this is the base case of our solution. Now comes the part of options. What options we were having? Basically, we were having the whole array as our options, right? Because we were having all these three branches at the start only. So these all three were the options for our particular solution. And even at each level, we were having at most three options only to explore. Means there was none level where we could say that no, we don't have three options at most. We were starting from that I only, and we were going till n, and that I was simply that particular element only which was from, means if we were having node as 1, right, and this node was at 0th index, right? So all the branches which were going down were simply having options this 0 to n, 0 to n, 0 to n, right? But then comes up this 2, then we were having options from 2 to n, 2 to n, right? Uh, Basically it was 1 because it is at index 1, right? So that's why at each branch we were having the whole input array as our option, right? Now comes the part for this particular recurrence relation. For this particular recurrence relation, it was, as I told while drawing that recursive tree, that how we were required to form a recurrence relation was, means how the steps were going in deeper and deeper was because of this fact that target minus candidate of I and that I was as it is. That's why we were having these options. Means everything was starting from that particular index only. That means it was passing I only in its recursive function and the target minus candidate of I. This particular thing which was there, because of that only we were having those branches, means 5 minus 1, then 4 minus 1, then 3 minus 1, which was being there, right? So this is how the recurrence relation would be made for our question. So now let's come to the part of the coding, and after that I'll explain you for the time complexity. So for the coding part, uh, is that same? Yeah. So for the coding part, now the thing is that this particular is the main Leetcode function which was being given to us. So what we have taken is we have taken a vector element. Why we have taken this? So that we could put all those temporary vectors which were being there. Means then we were making all this basically when it is much farther. Yeah. So basically in this recursion tree only, when we were having these branches, so these particular vectors. So these particular vectors are temporary vectors which are required to store at this temporary states, right? So that's why we are required to have this particular elements vector. Then we are having this particular result, which is the main result, vector in result, right? And then what we are doing is we are sorting this particular candidate's input, which is being there, right? And why we were sorting this particular candidate array was so that we could easily get all the combination in such a manner like a 2, 3, 6, and 7 as something like that. We could take 2 and then 3 and then 6 so that it could add up easily to 7. But if the elements are being scattered, like 6 is there, then 7 is there. So we could miss out some of the possible combinations here, right? Because when it simply comes to a particular stage that, yeah, now the the target minus the present element is going to negative, then we are discarding at that moment. So that's why it is required to sort this particular array. Now comes the part, uh, okay, now comes the next part, that is here. This was simply like that vector int elements, right? And then these two are simply those auxiliary arrays which are being taken for our answer. Now we are sorted, and then we are calling this particular function. How we are calling? We are simply passing this input vector, and then we are passing the result vector int, and then we are passing the elements which is being there. We have taken for our temporary purpose, and then we are passing this particular target which was input given to us by the user, and then we are having the 0, basically the starting index. Now the first thing is, if a target is equals to 0, basically this is the base case, then we will simply push that to our result, right? So this is that particular part which was there for a loop, and then present pushing the present element into a temporary element vector, and then this is that recursive function which is being there. Here the main part is for this target minus candidates of I and this I. So these are the main highlights of this function which is making possible that recursive tree. And then at the end we are backtracking so that we could easily reach to that particular stage of our element vector where we could explore out all other possible elements. Basically, we could skip this particular part if we are not passing our elements with this particular and. Means if we are not passing this by reference, then we could skip this particular part. But as I'm passing it, so yeah, I'm writing this here. So this was the whole code for this particular solution. Now comes the part of the time complexity. So let me explain you the time complexity of this solution. For the time complexity part, the thing is that I've searched a lot for the same. Like it was really ambiguous for me to get to know about all possible things which were being there because of two recursive function calls, but I have taken just one recursive function call, so that's why I explored a lot for time complexity. Now, you have already seen that how the recursive tree is like, right? So now here, the recursive tree is like this, where we are having the depth equals to target upon the minimum element, right? How this is possible? See, when we are having target as 8, right, and our minimum element in this particular array is 1, right? So if we divide it, means if we divide 8 by 1, then it will be simply 8 only. But if we are having the minimum element as 2, means if we discard the 1, then the maximum depth till which it can go is that particular 8 by 2, that is, it will go till 4 steps only, right? So that's why the maximum depth it could attain is target divided by minimum element. So that's why I've taken that particular depth. Now about the width of this particular recursive tree which I've made, because each node could have at max n child, right? So here, see this one. This one is and n is equals to 4, right? So at max, how many childs it could have? The one itself, right? This is the first child, then this is the second child, this is the third child, and this is the fourth child. So this is the at max it could have n childs. This is the scene. Means whatsoever node we'll pick up, right? So at max it could have the n child, and yeah, it will surely have less than that at subsequent levels, because here too it will be having the only 3 childs, and that also in that case when it encounters some element which is being less than the target. If it is not less than the target, then surely that element would also be skipped. So I'm giving you the upper bound that yeah, it could have at max n child only, and that is the possibility. If it wouldn't be having at most n child, then surely we couldn't give it this cap that yes, it is having at most n child. So as it could have at most n child, right? So this particular recursive tree is acting like an Henry tree, right? So if it is acting like an Henry tree, so in that manner, we could simply check that for number of nodes at each level, and we have total d levels, right? So if it is acting like an Henry tree, so we could simply do DFS in an Henry tree, right? And for doing DFS in Henry tree, the time complexity of that particular Henry tree is order of n, right? Where n simply refers to the number of nodes, right? So here what we were required to do was to find out the number of nodes in this particular recursive tree. And because of that only, how we can calculate the number of nodes in an Henry tree. Thus, it reduces to calculating number of nodes for doing DFS traversal in Henry tree. So that's why the time complexity would be simply n raised to power 0 plus n raised to power 1. That is summation of NCD. That was the thing. And that's why it simply changed to n raised to power d plus 1 minus 1. This was the maximum number of nodes which it could attain, and the minimum number of nodes which it could attain was n raised to power d. So this is what the time complexity could be. And the space complexity is simply the depth of this particular recursive tree, that is target upon minimum element. Right? So this is the space complexity, and here minimum element is simply strictly greater than 0. So this is about the space complexity, but there is one more context of this particular time complexity. But in context of selecting subsequences, we could select NCK subsequences from n elements, where subsequences could be at max k size, right? Because here we are simply selecting subsequences from the given number of elements in that array, right? So in that context, the time complexity would be simply k into summation of NCK, right? Because at max a particular subsequence can take the size k. So that's why it is simply k into summation of NCK, where it is simply equals to k into 2 raised to power n minus 1, which is at the end equals to 2, which is at the end equals to this. That is this particular. But now another thing which is there is, if target is big, right, then it will be simply having this particular time complexity. But if the target is small, then the time complexity will be simply n raised, not n into, but n raised to power target by minimum element. Means this would be the better upper bound. And now what the reason is for all this? Because in this first part, when we do this particular, then it is simply less than this particular, because our target is bigger, right? And one more thing here is that we are giving all these as upper caps only, and that upper caps are also not the exact upper cap. That is, it is not the type bound which we could give to this particular question, right? So that's why when the target is basically bigger, then we are having this particular time complexity for this particular question. But if the target is smaller, then in that context, we are having this particular as the time complexity of a solution. Because whatsoever upper bound we are giving to this particular question, that is not exactly the tightest bound, and the time complexity is basically much smaller than what we are giving. So that's why that is the case we are taking the time complexity in this manner. So at the end, the time complexity for this particular solution is simply minimum of n into 2 raised to power n, comma n raised to power target minus minimum element. So this is the basically time complexity of this particular question. But now one more thing is there that surely it will come up to mind that why we are considering the two time complexity, right? We where we are because of the fact that either one of them is not a tighter upper bound. The way I have explained here. So to start it simply like we could say that the time complexity is order of n into k. Why order of n into k? We can simply see here means in this particular recursive tree we can simply see this particular the depth and this particular width, right? So we are simply multiplying the depth into width, that is n into k, where n is the number of elements in the array and k is equal to number of subsets, not basically the subset but the subsequences. And okay, let me correct it only. Now here it is not subsets but the subsequences which is having some less than equals to target. We don't know the value of k, this is totally dependent on target input, right? So that's why the time complexity, so that's why here time complexity is simply like n into k, where k could be simply 2 raised to power n, right? That is that particular first case, or the k could be n raised to power target divided by minimum element minus 1. That is the whole complexity would be simply like this, right? So that's why we are having the time complexity equals to this, that is minimum of these two particular time complexities. We are having the time complexity for this particular question. But the space complexity for this particular question is target upon minimum element only, because that could be the maximum depth which we could have for a recursive stack, which will be calculating the answer for this question. So this was a little bit research and so on which I did for this particular question. And yeah, that's all for this particular question. I hope I have explained you in right manner, because I know this particular research that I did, it is good enough. But if you have any doubt, you could simply comment out, or if you have any other suggestion for this, you could simply say. And this was all for this particular video. Thank you.